Welcome to our exploration of noise in communication systems. In our daily lives, we rely on communication systems to share information, ideas, and emotions. However, these systems are not always perfect. One of the main challenges that can disrupt the flow of information is noise. Noise refers to any unwanted interference that distorts or interrupts the message being transmitted. Whether it's a crackling phone line, static on the radio, or even background chatter during a conversation, noise can make it difficult to understand the intended message. In this video, we'll dive deep into what noise is, its sources, and how it impacts communication. Start by defining noise in the context of communication systems. Noise is any unwanted signal that interferes with the transmission or reception of the intended message. It can occur at any point in the communication process, from the sender to the receiver. Noise can be random or systematic, and it often results in a loss of information or a decrease in the quality of the message. Understanding the nature of noise is crucial for designing effective communication systems that can minimize its impact. Noise in communication systems can be classified into several types. The most common categories include thermal noise, intermodulation noise, crosstalk, and impulse noise. Each type has its own unique characteristics and sources. For example, thermal noise is caused by the random motion of electrons in a conductor, while crosstalk occurs when signals from one channel interfere with another. By identifying the type of noise present, engineers can develop targeted strategies to reduce its effects. Thermal noise, also known as Johnson-Nyquist noise, is a fundamental type of noise present in all electronic devices. It arises from the random movement of electrons within a conductor, which generates a small continuous background signal. This noise is unavoidable and increases with temperature. In communication systems, thermal noise sets a lower limit on the smallest signal that can be detected, making it a critical factor in system design. Intermodulation noise occurs when signals at different frequencies mix together, creating new frequencies that were not present in the original signals. This type of noise is especially problematic in systems that handle multiple signals simultaneously, such as radio transmitters and receivers. Intermodulation noise can cause distortion and make it difficult to separate the original signals, leading to a loss of information. Crosstalk is a type of noise that occurs when a signal transmitted on one channel creates an undesired effect on another channel. This is common in telephone lines and data cables, where signals can leak from one wire to another. Crosstalk can result in overlapping conversations or data errors, reducing the clarity and reliability of communication. Engineers use shielding and twisted pair cables to minimize crosstalk. Pulse noise is characterized by sudden, short bursts of unwanted energy. It can be caused by electrical switches, lightning, or other abrupt changes in the environment. Impulse noise is particularly disruptive because it can corrupt entire blocks of data or cause momentary loss of signal. Communication systems often use error correction techniques to recover from the effects of impulse noise. Noise can originate from a variety of sources, both internal and external to the communication system. Internal sources include components like resistors and transistors, which generate thermal noise. External sources can be natural, such as lightning or cosmic radiation, or man-made, like electrical machinery and radio transmitters. Identifying the source of noise is the first step in developing effective mitigation strategies. Environmental noise refers to unwanted signals that originate from the surrounding environment. This can include electromagnetic interference from nearby electronic devices, power lines, or even solar activity. Environmental noise is often unpredictable and can vary depending on location and time. Communication systems must be designed to withstand these fluctuations and maintain reliable performance. Man-made noise is generated by human activities and technology. Common sources include electrical motors, fluorescent lights, computers, and wireless devices. In urban areas, man-made noise can be a significant problem, especially for sensitive communication systems. Engineers must consider these sources when designing and installing communication infrastructure. Natural noise sources include phenomena such as lightning, solar flares, and cosmic background radiation. These sources are beyond human control and can cause significant disruptions, especially in long-distance or satellite communications. Understanding the patterns and intensity of natural noise helps engineers design systems that can adapt to changing conditions. Analog communication systems are particularly vulnerable to noise. Since analog signals vary continuously, any interference can directly alter the signal's amplitude or frequency. This can result in static on a radio, hiss on a phone call, or distortion in audio and video transmissions. Engineers use filters and shielding to reduce the impact of noise in analog systems. Digital communication systems are generally more robust against noise, but they are not immune. Noise can cause errors in the transmission of binary data, leading to corrupted files or dropped connections. Error detection and correction codes are commonly used to identify and fix these errors, ensuring the integrity of digital communication. Signal-to-noise ratio, or SNR, is a key metric in communication systems. It measures the strength of the desired signal relative to the background noise. A high SNR means the signal is much stronger than the noise, resulting in clear communication. A low SNR indicates that noise is overpowering the signal, making it difficult to understand the message. Improving SNR is a primary goal in system design. Bandwidth refers to the range of frequencies a communication system can transmit. The amount of noise present in a system often increases with bandwidth, as more frequencies are exposed to potential interference. Engineers must balance the need for high bandwidth with the risk of increased noise, using techniques like filtering and modulation to optimize performance. Modulation is the process of varying a carrier signal to transmit information. Different modulation techniques have varying levels of resistance to noise. For example, frequency modulation (FM) is less susceptible to amplitude noise than amplitude modulation (AM). Choosing the right modulation method can significantly reduce the impact of noise on communication. To combat noise, communication systems use error detection methods such as parity checks and checksums. These techniques allow the receiver to identify when data has been corrupted by noise. Once an error is detected, the system can request a retransmission or use error correction codes to recover the original message. Error correction techniques go a step further by not only detecting errors but also correcting them. Common methods include Hamming codes and Reed-Solomon codes. These techniques add redundancy to the transmitted data, allowing the receiver to reconstruct the original message even if some bits are corrupted by noise. Physical techniques like shielding and grounding are essential for reducing noise in communication systems. Shielding involves enclosing cables or devices in conductive material to block external electromagnetic interference. Grounding provides a safe path for unwanted signals to dissipate, protecting sensitive equipment from noise. Twisted pair cables are commonly used in communication systems to reduce crosstalk and electromagnetic interference. By twisting the wires together, the cable cancels out much of the noise that would otherwise affect the signal. This simple yet effective technique is widely used in telephone and network cables. Optical fiber communication offers a significant advantage over traditional copper cables when it comes to noise immunity. Since optical fibers transmit data using light rather than electrical signals, they are immune to electromagnetic interference. This makes them ideal for high-speed, long-distance communication where noise can be a major issue. Wireless communication systems face unique challenges when it comes to noise. Signals transmitted through the air are susceptible to interference from other wireless devices, weather conditions, and physical obstacles. Engineers use advanced modulation techniques and error correction to maintain signal quality in these environments. Satellite communication systems operate over vast distances and are exposed to a wide range of noise sources, including cosmic radiation and atmospheric disturbances. Engineers must design robust systems that can handle these challenges, often using powerful error correction and signal amplification techniques. Mobile communication systems, such as cell phones, must contend with a variety of noise sources, including interference from other devices, buildings, and even moving vehicles. Techniques like frequency hopping and adaptive filtering help maintain clear connections in these dynamic environments. Data transmission over networks is vulnerable to noise, which can cause packet loss, delays, and errors. Protocols like TCP/IP include mechanisms for detecting and correcting errors, ensuring that data arrives intact even in noisy environments. Reliable data transmission is essential for everything from email to video streaming. Voice communication, whether over the phone or internet, is highly sensitive to noise. Background sounds, echo, and static can all degrade call quality. Modern systems use noise suppression algorithms and echo cancellation to improve the clarity of voice communication. Video communication systems, such as video calls and streaming, can also be affected by noise. Visual artifacts, pixelation, and audio lag are common symptoms. Compression algorithms and error correction help maintain video quality even when noise is present. Wireless networks such as Wi-Fi are particularly susceptible to noise from other electronic devices, physical barriers, and even weather conditions. Channel selection and signal boosting are common strategies to reduce the impact of noise and maintain strong connections. Wired networks, while generally more stable than wireless, can still experience noise from electromagnetic interference and crosstalk. Using high-quality cables and proper installation techniques helps minimize these issues and ensures reliable data transmission. Broadcast communication, such as radio and television, must deal with noise from a variety of sources. Atmospheric conditions, electrical equipment, and even sunspots can introduce noise. Broadcasters use powerful transmitters and error correction to ensure their signals reach audiences clearly. Industrial environments are often filled with electrical machinery that generates significant noise. Communication systems in factories and plants must be designed to withstand high levels of electromagnetic interference. Shielded cables and robust protocols are essential for reliable industrial communication. Medical communication systems, such as those used in hospitals, require extremely high reliability. Noise can interfere with critical data transmission, affecting patient care. Specialized shielding and error correction are used to ensure that medical information is transmitted accurately and securely. Financial institutions rely on fast and accurate communication for transactions and trading. Noise can cause delays or errors, leading to financial losses. High-speed networks with advanced error correction are used to minimize the impact of noise in financial communication. Emergency communication systems must function reliably even in the presence of high noise levels. Whether it's during a natural disaster or a power outage, these systems use redundant channels and robust error correction to ensure that critical messages get through. Military communication systems operate in some of the most challenging environments, where noise and interference can be used as deliberate tactics by adversaries. Secure encryption, frequency hopping, and advanced error correction are essential for maintaining reliable communication in these situations. Space communication systems must contend with cosmic noise, solar radiation, and vast distances. Signal attenuation and delay are significant challenges. Engineers use powerful transmitters, large antennas, and sophisticated error correction to ensure successful communication with spacecraft. Underwater communication relies on acoustic signals, which are highly susceptible to noise from marine life, ships, and environmental factors. Techniques like frequency selection and signal processing help reduce noise and improve the reliability of underwater communication. Optical communication systems, such as fiber optics, are generally immune to electromagnetic noise but can still be affected by physical disturbances and imperfections in the fiber. Engineers use high-quality materials and precise installation techniques to minimize noise in optical systems. Satellite TV signals travel long distances and pass through the atmosphere, where they can pick up noise from weather, solar activity, and other sources. Error correction and signal amplification are used to ensure viewers receive clear, uninterrupted broadcasts. Internet communication relies on a complex network of wired and wireless connections, all of which can be affected by noise. Protocols like TCP/IP and error correction algorithms ensure that data is transmitted accurately, even when noise is present. Social media platforms depend on reliable communication networks to deliver messages, images, and videos. Network congestion and noise can cause delays or loss of content. Content delivery networks and error correction help maintain a smooth user experience. Cloud communication involves transmitting data to and from remote servers. Noise in the network can lead to delays, data loss, or synchronization issues. Redundant connections and robust error correction are used to ensure reliable cloud communication. As communication technology evolves, new methods for reducing noise are being developed. Machine learning algorithms can now detect and filter out noise more effectively than ever before. The future promises even more robust and reliable communication systems. In summary, noise is an unavoidable challenge in all communication systems. By understanding its sources and effects, engineers can design systems that minimize its impact. Techniques like error correction, shielding, and advanced modulation are essential tools in the ongoing battle against noise. Thank you for joining us on this journey through the world of noise in communication systems. As technology continues to advance, our ability to manage and reduce noise will only improve. Clear, reliable communication is essential for connecting people and powering progress in every field.